So far, we've covered the first two major chapters in physics, kinematics and forces. In this video, we will look at the next major concept, work. In this course, we've seen several instances where an object feels multiple forces but doesn't move. For instance, this coconut feels two forces, weight pointed down and normal force pointed up. But these forces exactly cancel out. The coconut feels no unbalanced force, so it cannot accelerate from rest. So even though there are two forces acting on the coconut, neither one is actually causing any displacement. For an object to accelerate, it needs to feel an unbalanced force in accordance with Newton's first. Here, we see a coconut falling from a tree. This coconut feels the weight force, the force of gravity pulls the coconut downward, but there's no force pushing the coconut upward, nothing to oppose or counter the weight, so it accelerates. We can say the weight force caused the downward acceleration, or more specifically for our purposes, the weight force caused the downward displacement. We can measure the practical effect of a force by observing the displacement that it causes. The practical effect of a force is called work. Work depends on force and displacement. Remember that force and displacement are both vectors. They both have sizes and angles of orientation. The calculation for work is like this. Take the size of the force, multiply that by the size of the displacement, then multiply that by the cosine of the angle between them. My Physics 103 students should recognize this operation. They would symbolize this operation as the dot product of force and displacement. Now, a few characteristics of work. Work is a unique quantity in all the physics we've done so far because it is a scalar, not a vector. It has no direction. We never write work with an I hat or a j hat. I will take off points if you do. Since it's a scalar, the symbol for work is a capital W without a vector arrow on top. This is to distinguish it from weight, which has a vector arrow since forces are always vectors. Work is the product of a force and a displacement. The units of work are therefore the units of force, newtons, times the units of displacement, meters. So work is measured in Newton meters. But it gets a little awkward to keep saying Newton meters. So instead, we call this unit the joule. So we can say work is measured in joules. When we are solving for the work performed by a single force, this definition of work will serve us nicely. Consider this situation. An object sits on a frictionless floor. You push it with 5 newtons of force. Your force is parallel to the floor. The object moves 2 meters. How much work did you do? Let's start by drawing a picture. You are pushing this object with a force of 5 newtons. And you're eventually going to push it across the floor, which, by the way, is frictionless. Here is the origin. And the rightward direction is x. This photo over here is photo 1. And this photo over here is photo 2. Between these two positions, the object has moved by 2 meters. We want to find out what is the work being performed on this object by you. If we were to draw out the free body diagram for this object, it would look something like this. This step is technically optional, but for the sake of completeness, I would like to do it. So, this object would feel weight pointing down, normal force pointing up, and your push, that is the applied force, pointing rightwards. So this would be the x direction, that would be the y direction. Now we're being asked to find out how much work was performed between photo 1 and photo 2. So let us use our formula for work. Work is equal to the size of the applied force times the displacement of the object times the cosine of the angle between those two quantities. Now, the applied force was 5 newtons. You pushed it with 5 newtons rightwards. So we could write that as 5 I hat newtons given the way that the x-axis is pointing. The displacement of this object is also rightwards. So that means that the displacement was going to be 2 meters, and because it's also in the x direction, we would say this is 2 I hat meters, times the cosine of the force is along the x-axis, that is 0 degrees, and the displacement is also along the x-axis, which would also be 0 degrees. So you could write it like this: 0 degrees minus 0 degrees. So this is all going to simplify to 5, the absolute value of the force, or the size of the force is 5. The size of the displacement was 2, times the cosine of 0 degrees. Now, the cosine of 0 degrees is 1. So the work is going to be 5 times 2 times 1, which all works out to 10 joules. So this is the quantity of work that you did in pushing this object with a force of 5 newtons over a displacement of 2 meters. The definition of work is also easy to use when the force points at an oblique angle. Consider this variant on the previous example. An object sits on a frictionless floor. You tie a rope to it and pull with 5 newtons of force. The rope is angled 30 degrees above the horizontal. The object moves 2 meters. How much work did you do? In this case, we have an object which is sitting on the floor, and you are dragging it using a rope. So if this is photo 1 over here, where you just start moving it, then this over here is going to be photo 2, the location that you have moved it to. This back surface here is the origin, and I will consider rightwards to be the positive direction. So now our object has moved 2 units, or 2 meters, in the positive x direction. So that would be 2 I hat for its displacement. Now, if I were to draw the free body diagram on this object, it would look something like this. Here's the object. we have weight pointed down, we have normal force pointed up, and we have, in addition to both of those, the tension force. The tension force points at an oblique angle. Now the tension force has a size of 5 newtons, but this angle over here is now 30 degrees. Once again, we can draw in our x-axis and the y-axis. Like I said, drawing a free body diagram isn't strictly necessary for work questions, but it does make it a little bit easier to visualize the forces and the directions of the forces. So now we have an object that is moving purely in the x direction, but the tension is not pointed along the x direction, it's pointed 30 degrees above the horizontal. Now, let's go ahead and let's solve for work. Let's say I do it over here. Work is equal to the size of the force, in this case that would be the tension force, multiplied by the size of the displacement, multiplied by the cosine of the angle between them. So, the size of the force is 5 newtons, same as before. The size of the displacement is 2 meters, also same as before. But now, the cosine between the tension and the direction of motion is in x, tension is 30 degrees above x, is 30 degrees. So the amount of work that was done is 5 times 2 times the cosine of 30 degrees, which is 8.66 joules. You'll notice that this is a smaller amount of work than what we got in the previous question. In the previous question, it was 10 joules. Here, it's 8.66. So the greater the misalignment between the tension force, or whatever the force is, and the direction of motion, the smaller the quantity of work. The bigger this angle, the smaller the amount of work. You might be wondering at this point if it's possible for the quantity of work to be 0. In fact, this can occur quite easily, and there are 2 main reasons why. Here's the first possibility. In this animation, our protagonist is pushing at an object but isn't able to budge it by a millimeter. How much work are they doing? Well, work equals force times displacement. If they aren't moving the object, the displacement is 0, which means the work is also 0. If an object doesn't move, the work is 0. A second possibility can be illustrated with this example. You carry a 10 kilogram box a horizontal distance of 5 meters. You keep it a constant height of 1 meter above the floor. How much work does the weight force do as you carry the box? In this question, you are carrying a 10 kilogram object. So, initially, you will hold it a certain distance above the ground, and you will move it horizontally, keeping it at that same height above the ground. So, in both of these cases, the distance from this object to the ground is 1 meter, but the object itself has horizontally moved by a distance of 5 meters in the positive x direction. So if we were to draw the free body diagram for this object over here, it would look something like this. This object has a normal force coming from your hands, so that would be pointed up, and that's going to counter the weight force, which is pointed down. And you're applying a force to push it rightwards from 0 meters to 5 meters. The rightward direction is positive x. The upward direction is positive y. Now, we were being asked to find out how much work the weight force is doing. So first we need to find out how big the weight force is. The weight force, which is symbolized as the W with a vector sign, so that we don't confuse it with work, which doesn't have the vector sign, is equal to mass times gravity. The mass is 10 kilograms. Gravity is the familiar 9.81, which works out to 98.1 newtons. So that is the force of weight. Now the next thing to do is to figure out what the work being done by weight is. So let's go ahead and do that. The work, notice that this is written as a W without the vector hat to show that this is work, which is not a vector. This is a scalar, so we don't put a vector hat, is equal to the size of the force multiplied by the displacement of the object multiplied by the cosine of the angle between the displacement and the force. Now, since we're interested in the weight force, the force is going to be 98.1. So we would write this as 98.1 times the displacement of the object, which is 5, times the cosine between these two vectors. So the displacement of the object is 5 meters in the x direction, but the weight force is pointed in the negative y direction. So the angle between the displacement, which is x, and the weight force, which is y, is 90 degrees. So to review, we found out what the weight force was. We plugged that into the work equation in order to solve for the work which this weight force is going to do. Let's go ahead and calculate this. The cosine of 90 degrees is 0. So that means that this entire calculation now becomes 98.1 times 5 times 0, which is, of course, 0 joules. So that means that the force of weight did not do any work at all in moving this object over the 5 meters. So the object did move, but weight had no role to play in that motion. Its work is 0 joules. When an object moves horizontally, gravity does no work on it. More generally, whenever the angle between the force vector and the displacement vector is 90 degrees, the cosine works out to 0, so the work is also 0. A surprising place where we see this effect is in uniform circular motion. In uniform circular motion, the velocity, and therefore the displacement of the object, is tangential to the circle. But the centripetal force points toward the center of the circle, 90 degrees away. The force and the displacement are always at 90 degrees from each other throughout the whole process. As a result, uniform circular motion involves zero work. Now, let's consider this situation. A 10-kilogram box slides down a 5-meter ramp oriented at 30 degrees. The coefficient of kinetic friction between the two surfaces is 0.15. What is the force of friction? And how much work did friction do? In this question, we have an object that is sliding down a ramp. The ramp has an inclination of 30 degrees. The object has a mass of 10 kilograms. The length of the ramp is 5 meters. And there is kinetic friction in this question. The coefficient of kinetic friction is 0.15. So knowing all of this information, we want to find out first, how big is the force of kinetic friction? And secondly, what is the work done by kinetic friction? To do all this, we first need to draw a free body diagram. In this diagram, weight would be pointed down. The normal force is always pointed at 90 degrees to the ramp, so it would be pointed off in this direction. And since the object is sliding down the ramp, that means that the force of kinetic friction must be pointed up the ramp. We can set our axes now. In a ramp question, we always set the y-axis to be in line with the normal force and the x-axis to be in line with the surface of the ramp. This leaves only the weight force not aligned with one of the two axes. Now, if this had been a level surface, the normal force would have pointed straight up. But since it's not a level surface, because this is tilted at 30 degrees, the normal force is also tilted 30 degrees away from the vertical, which means that the angle between the weight force and the y-axis must also be 30 degrees. Let's break the weight force into its components. This component over here, the one that's parallel to the x-axis, is opposite the 30 degrees. So this is weight sine 30. This one, which is along the y-axis, is adjacent to the 30 degrees, so this becomes weight cos 30. So that's our free body diagram. We are now ready to set up our force balance. Let's start with the y-axis. In the y direction, the total force will be given by the normal force pointed in the positive direction minus weight cos 30, which is pointed in the negative direction. But total force is equal to mass times acceleration. So that means that the normal force minus weight cos 30 must be equal to mass times acceleration. Now this object is not levitating off the ramp, nor is it collapsing into the ramp. There's no motion at all in the y direction. That means that this acceleration is 0. Now, let's go ahead and solve for the weight. The size of the weight force is given by mg, which is equal to mass 10 times g 9.81, which was going to work out to 98.1 newtons. Let's plug this information into our force balance. We now have the normal force minus 98.1 cos 30 degrees is equal to mass times acceleration, but this entire right side works out to 0. So now all we have to do is move this 98.1 cos 30 to the other side. And let's calculate that in the meantime. 98.1 cos 30 gives us 84.96. So the normal force is equal to 84.96 newtons. Just for the sake of clarity, I'm going to highlight this 98.1 where it appears. I'm going to give a purple underline to the normal force so that we're able to track that along as we solve this puzzle. We've now solved for the normal force. The next step is to look at the x direction and look specifically for the friction force. Now, we know that the force of kinetic friction is solved as the coefficient of kinetic friction multiplied by the size of the normal force. The coefficient of kinetic friction is 0.15. The normal force is 84.96. So, this is that same 84.96 that we found out just a moment ago. 0.15 times 84.96 gives us 12.75. Newtons. I'm going to put an orange underline under the kinetic friction. So we have now solved for how large the force of friction is. The next thing to do is to solve for the actual work of friction. The work of friction is given by the force of friction multiplied by the displacement of the object multiplied by the cosine of the angle between them. So the size of the force of friction is 12.75. The displacement of the object is 5 meters times the cosine of the displacement is down the ramp, but the force of friction points up the ramp. So that means that these two forces are 180 degrees apart from each other. Whenever you have two forces pointed in opposite directions, that means that the angle between them is 180. If they pointed in the same direction, it would be 0, but if they point in opposite directions, it's 180. So now that we have all of this information, and again, I'm going to track this force, this friction force, which we just solved for, we can solve for the work. So 12.75 times 5 times the cosine of 180 degrees is negative 63.72. And that's in joules. When a force points opposite the direction of motion, the work is negative. More generally, if the angle between force and displacement is more than 90 degrees, the force performs negative work. The classic example of a force that does negative work is kinetic friction, but there are others. One last quantity which is useful to know is power. Power is calculated as work divided by time. It measures how quickly work is done. Like work, power is a scalar. Since work is measured in joules, power is measured in joules per second. But again, it's a little inconvenient to keep saying joules per second, so we'll call the unit of power by another name, the watt. 1 watt is 1 joule of work performed every second. Be careful not to confuse the symbol for watts with the symbol for work. If you switch on a 50-watt light bulb, it is performing 50 joules of work every second. And if you go to the gym, a fast exercise will test not your work output, but your power endurance. Consider this example. A weightlifter applies a 500 Newton force to a barbell. They lift the barbell by 1.5 meters. How much power did they exert if they lifted the barbell in 2 seconds? In this question, we have a weightlifter, and this weightlifter is going to lift a barbell. So photo 1 corresponds to the barbell being on the ground, and photo 2 corresponds to it being lifted off the ground. I'm going to set upwards as being the positive direction, and I'm going to set the origin as being the ground. The weightlifter exerted a force of 500 newtons, and the distance that the barbell traveled off the ground was 1.5 meters. The weightlifter took 2 seconds to elevate the barbell. So what we would like to find out is, what is the power that the weightlifter exerted? Let's start by figuring out the work. Work is equal to the force multiplied by the displacement multiplied by the cosine of the angle between them. The force that the weightlifter exerted was 500 newtons. And if we want to be specific, because it's 500 newtons point in the positive direction, we should put a j hat over here. The displacement of this object was 1.5 meters, also in j hat. And because both of these vectors point in the positive y direction, the angle between these two vectors is 0. So all of this is going to work out to 500 newtons times 1.5 meters times the cosine of 0, which is 1. So the work is going to be 500 times 1.5, which is 750 joules of work to elevate these barbells. Now as for the power, power is equal to work divided by time. So if our weightlifter over here performed 750 joules of work in a span of only 2 seconds, that means that the power exerted was 750 divided by 2 is 375 watts. Joules divided by second gives us watts. And this is the power that our weightlifter exerted to raise these barbells in only 2 seconds. If you're in my 101 class, you can stop here. My 103 class should watch this last bit. So far, we've assumed that the force acting on the object is constant. But what happens if the force is variable? In that case, the dot product turns into an integral. We integrate the force between the endpoints of motion. Here's an example. A probe is in space, initially at rest. Its thrusters turn on. They turn off after the probe has traveled 3 meters. The force of the thrusters is given by the equation F equals negative x squared plus 9. How much work did the thrusters do? In this question, there is a rocket or a probe, and it turns on its thrusters briefly. At some point later, it turns off its thrusters. And what we were told was that the distance that it travels from the point where it turns on its thrusters to the point where it turns off its thrusters is 3 meters. We were also told that the force of the thrusters was given by negative x squared plus 9. And the way that I've drawn this force vector would be in I hat, and this whole thing would be measured in newtons. This is a variable force. So we would like to find out what is the total work done. Whenever you have a variable force, the work is calculated by integrating the force over the displacement. So the initial position was 0. The final position was 3. The force is negative x squared plus 9 dx. So we just need to integrate this expression over here. Negative x squared is going to turn into negative 1/3 x cubed, and the plus 9 is going to turn into 9x. And this whole thing needs to be evaluated from 0 to 3. So let's see what that works out to. If I plug in 3 for x over here, I get negative 1/3 times 3 cubed plus 9 times 3 minus negative 1/3 of 0 cubed plus 9 times 0. Obviously, this second term is going to completely cancel out. So we're left with negative 1/3 times 3 cubed is 27 plus 9 times 3, also 27, which works out to negative 9 plus 27, which is 18 joules of work. So the thrusters performed 18 joules of work as they acted on this probe and pushed it over this distance of 3 meters. Just like work has a slightly different definition under calculus, so does power. If work is not constant over time, the power has to be calculated not as work divided by time, but as the derivative of work with respect to time. But work equals force times displacement. If the force is constant, then this becomes force times the derivative of displacement, which is velocity. So power can be calculated as force dot velocity. In this video, we saw several examples of how to calculate work. In the next video, we'll explore the closely related concept of energy.